Okay, so excuse me, I had some technical difficulties and towards the end of the last video. So I lift off here. We have this polynomial. We distribute it. So now we have something that's more of our standard form of the polynomial. Right? And we see here it's in decreasing order in terms of the exponents. So we've identified that n is equal to 5. So we have a polynomial of degree 5. Right, so the next thing is to identify the end behavior. And again, when you hear end behavior, what you should be associating that with is what happens as x goes to infinity and x goes to negative infinity. Now again, for each polynomial, there might be some interesting behavior in what's called local behavior, kind of near and around the origin, but I'm not concerned about that here. Right? What I'm going to be focused on is what happens as x gets larger and larger, and to focus or to determine that, the driving factor behind that is this leading term. Okay, so what I know from here, it's odd, and this is a positive coefficient, so it has this general shape at the ends. Okay, and as we can see from the graph, as x goes to infinity, the values of f of x also go to infinity. Now as x goes to negative infinity, the values, those go decrease, they get more and more negative, so they go to negative infinity. Okay, and that's how we would determine one degree, and that also helps us determine the end behavior. All right, now let's so we looked at end behavior. Now on the other end, we have what's called local behavior. Right, so local behavior, what we're going to define that as and so we took a look at what happens towards the end as x goes to infinity and negative infinity. But here when we call something local behavior, we're going to look at two quantities in particular here. We have x-intercepts. So those are these right here. Right, and also something that are called turning points. Okay. All right. Now here we see in terms of the x-intercepts, and those are, excuse me, those are self-described, right? X-intercepts wherever it crosses the x-axis. And then turning points. Now these are something probably we have not at least talked about in any algebra class. Here, so a turning point, if you notice what's happening here is there are two turning points for this function. We have the function is increasing, then it reaches this point here, and it's no longer increasing, right? Now it's not a maximum like we discussed with quadratics, because as we see out here, these values they get bigger and bigger, but it kind of looks like a maximum. In fact, this is what's known as a local maximum, right? Where any values that are near there, and again, that word near, right, depends how you want to define as near. So, but we can just say you're close by here, right? Anything else is smaller than this value, right? So it signifies as a change, a turning point in the function. It goes from increasing once it reaches this local max here, then it goes to decreasing. Right, and then it decreases, and notice here we arrive at another turning point, right, where this is not a minimum because these values here are smaller, right, but it's what is a local called a local minimum, right, where the values near there, right, are larger than this local minimum value, right? But it turns in the sense that it goes from decreasing, reaches this low point, local, and then it starts to increase, right? All right. So that is what we call turning points. Now, in this setting here, we won't really go into finding these turning points. We just want to know that they exist, right? In fact, in calculus, we'll spend a lot of time actually determining what these local max and min are. But for now, we'll just label these as turning points. All right, now if we notice here, there are 3 x-intercepts and 2 turning points. Right, now that's we want to establish here a relationship between the turning points and the intercepts. All right, so here intercepts and turning points. Right. So a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. Okay, so we've established now, again, be careful of this wording. We'll have at most n x-intercepts. So it can have less, actually. It really just depends on the polynomial functions itself. Right? And n minus 1 turning points. But we know for a fact that, or this fact is establishing that there will not be more than n, right? So if we have a quadratic, right, there are at most 2 x-intercepts, right? And if we recall from our study in the previous section here, right, the quadratic function gave us at most those 2, right? But not always 2, right? Sometimes 0, sometimes 1, right? So keep that in mind, right? At most n, right? And at most and n minus 1 turning points. And we saw in the quadratic, right, it always had the same general shape. So it had n minus 1 turning points. Okay, so in this case, 1 turning point. And that was always guaranteed, that turning point, just because of the natural or the shape of the parabola. Right, but let's work out some examples here. All right, so here, so I want to find the x-intercepts of the following functions. All right, so let's say we had function in terms of t minus 1, t plus 2, t minus 3. All right. Okay, so keep in mind when we want x-intercepts, that means that y is equal to 0. In this case, f of t equal to 0. And so we want to determine when this is true. Okay. All right. Now, nice. This is in factored form here, right? So really, it comes down to solving. 2 is 2, so it's not going to affect this product here. But we have a product of 3 numbers. Or 4, I should say. The 2, the term t minus 1, t plus 2, t minus 3. All right. Now, in order for a product to be 0, that means one of the values needs to be 0. So here we have t minus 1 equals to 0, or t plus 2 equals to 0, or t minus 3 is equal to 0. So solving each one of those linear factors here, we get 3 zeros, right? T equals 1, T equals -2, T equals 3, which corresponds here in terms of our function here. This is, if I distribute all these, you'll get a cubic, right? The leading T, so we get a cubic function with 3 zeros, so at most 3. In this case, it has all 3. And actually, we can build a pretty good graph of this, right? Just based off of what we know here. So here I know it crosses the x-axis at 1, 3, and -2. All right. Not only that, I know it's a cubic, and based off of what this looks like, the leading coefficient, right, I'm going to multiply this by 2, right, is a +2. So what that tells me is that the end behavior looks something like this when it goes towards positive infinity. And then in between here, as x goes to negative infinity, the values of the function also go to negative infinity. All right, so I do get a pretty decent sketch here of this. And notice here that I have 2 turning points. And that makes sense, right? If it's a polynomial of degree 3, which in this case it is, then there is at most 2 turning points. In this case, there are exactly 2 turning points, from increasing to decreasing, and then from decreasing to increasing. Okay? All right, and again, end behavior from the leading term here. And looking at this, right, the leading term would be t times t times t, and then that 2t cubed. All right, so that's where I'm identifying this end behavior. All right. One thing I don't know is I don't really know the extent of how high these local min and local, or how low the local max go, or even the y-intercept. I just kind of drew a sketch there with a little more. We could find the y-intercept if we wanted to. At this point, right, we don't have the tools yet to determine these local max and local min. Right, that would come at in our calculus course. We would have the tools that'll help us find those rather quickly. Okay. All right, let's do one more example here. Okay, so here, for this example, I want to find the x-intercepts. Okay, so for this function here, we're going to have a cubic, right? If we distribute, so it's a quadratic, and I distribute the x, we'll get a cubic. But to find the x-intercepts, I actually want to factor. Right? So it looks like I can factor this in this form. Right? Okay, and then here we have, so x squared, positive 2x minus 4x, negative 2x, and the last one is negative 8. So our x-intercepts would be x equals 0, x minus 4 equals 0, or x plus 2 equals to 0. All right, and then solve. This one's already solved. Solving these linear terms, we get these 3 things here. Okay. All right. And similar to how we did in the previous example, we could build a pretty accurate graph of this function here. All right. Okay. Thank you.